Hello, everybody, to our new webinar this year concerning XRF fusion technology. My name is Rainer Schramm, and today I would like to introduce fusion a bit from another side than normally. That means I want to discuss what are the daily problems we always see when we want to do fusion, and we struggle to get a stable bead. And therefore I want to get some deeper into why we need fusion and what we can do to optimize it. Okay, let's start. So I will explain why we do fusion, what is our motivation, the fusion principle, what do we need to get a successful fuse bead, and some examples. If we look on the sample preparation techniques we normally use for XRF, we have very simple, we can use a sample cup where we normally can put liquids in or loose powders, or we could use the pressing technology to make a press pellet out of a powder, or we can dissolve the powder directly into glass to get a fuse bead. And of course, there are other techniques like we measure directly metal or plastic samples. But let's talk today about fusion and why do we need to do that. It has all to do with the penetration depth of the X-ray technology from our sample. It means how deep do we analyze our sample. And there we have the difference between a loose powder or press pellet or a fusion, that if we just have a powder in a sample cup or in a press pellet, that we have single particles lying in our analyzed sample. And that the X-ray, which comes from underneath, they just see the particles from which are lying on the measuring side and not particles which are deeper in the sample. And this is depending on the element you are analyzing. And for that, I put this table here from a cement sample, and the elements here are in the order of the penetration depth. That means the lightest element, sodium, is on top. And there we have a penetration of just 8 micrometers. While if we go to heavier elements like iron, we see that we already have a penetration of 174 micrometer. And if we think about that, the typical sample we grind in a disc grinder comes out between 50 and 100 micrometer particle size. And this means that here we just touch the downside to measure in the measurement, while here in iron we measure at least 3 layers of particles. And this is what we see when we do press pellets or loose powders, that we have quite a high error for the light elements. And this is because sometimes the element is lying in the first layer, and sometimes we find it in the second layer, and then it can't be seen by the X-ray. So this all has to do with this particle effects and how deep we measure into our sample. And so this also means that for these very light elements, we have limitations. The error we get there in a loose powder or press pellet is defined by this distribution of particles. And when we want to get it better, then we have to dissolve this completely. And this would mean, if we look on a fuse bead, this is like a liquid, like tea where we put sugar into, and it's completely dissolved then. That's the same here in a fusion. That means our powder is completely dissolved into that glass, and this is like into a liquid, so that we can assume we have a completely homogeneous distribution. And then if we analyze just the surface, this will be representative for the whole sample. While in a press pellet or loose powder, we still have this heterogeneous particle distribution, so that sometimes elements are thin and sometimes not. That's not the case in fusion. There we have really a homogeneous sample, and this is what we want to achieve. And this is the motivation why we invest time and money to do fusion when the precision and accuracy we get from a press pellet method is not enough. Okay, so how do we do fusion? The idea is always we need a glass powder, a glass where we want to dissolve our sample into. And so we mix this glass powder together with the sample. And we have to make a good contact between both, so mix very well. Then it is heated, it is brought to liquid, then it is homogenized, and after that we can pour it into a mold to get finally a stable glass out of it. What kind of fusion systems do we have? We could use either gas burner based, we could use a muffle furnace, or we could use an induction furnace. Today I want to talk only about gas burners and muffle furnace because we, for our application, don't use induction furnaces because the principle there is that the heat is generated in the crucible. And this means that while all these crucibles are a bit different, the heat is always a bit different, the temperature, and this brings a certain instability. And for special applications where we have volatile elements, you can't use that. So we need really very stable temperatures, like here in the muffle furnace or in the gas burner. And this is why we concentrate on these two techniques. But what do we need to make fusion? So we need, of course, a flux, this glass former, this glass powder. Then the sample has also to fulfill some requirements. Then it's a question, what is the dilution between sample and flux? Do we need any non-wetting agents we have to add? What temperature do we use? What time? How do we homogenize? Platinum ware is playing a role. And of course, how do we cool it down that we get a stable glass? So let's start with the glass powder. Typically today we use lithium borates, and you could also use borax sodium borates or just boron oxide. This is also okay, but typically the lithium borates are used. And if we want to see how the different fluxes, the different lithium borates are behaving, we need to have a look into that phase diagram. So how do we read that? Here we have the temperature, and here we have the amount of boron oxide we have, and you know that the lithium borates, what we typically have is lithium tetraborate or lithium metaborate. So this is then a mixture between lithium oxide and boron oxide. So we have to read this in this way, that everything over this line, so higher than this line, is liquid. So this is all liquid phase, and this is all solid phase. And that means if we have a certain ratio between lithium oxide and boron oxide, and we are liquid and we go down, then this is the solid phase we will get. So this is the ratio then of lithium borate and another component, so different borates we will find. For our flux, we have just to look in that range because this is the interesting range we have for lithium borates. And we start with pure lithium metaborate with a melting point from 849 degrees, tetraborate 917 degrees. And then we have two mixtures in between. 1/3 tetraborate will be here, and 1/3 metaborate will be here. So you see how the melting point is depending on the flux we are using. And it's not only the melting point, it's also the behavior of forming a stable glass. While lithium tetraborate is a glass former, so gives immediately a stable glass, lithium metaborate is not. It's just crystallizing, directly forming a crystalline solid. While if we cool down for lithium tetraborate and we cool down quick enough, we still have a liquid frozen into glass. That's how we can say it. Okay, so this is very important. So you have to look on the melting point here, and you have to look on how easy you get the glass and this is then better on the lithium tetraborate side. Of course, the lithium borates from nature are hygroscopic, but if we pre-melt them, that means they are once melted into glass and then ground again, then you reduce the surface, and in this way they are much more stable and you can directly use them from the bottle. And of course, nowadays we also have dust-free fluxes, so this is then even more healthier to use them. And these ones, for example, the bead fluxes, you can also use in dosing systems. So this is perhaps how we can think about it behaves into a liquid class. That means you will have this arrangement of boron cations and oxygen anions, which are then, of course, in a certain relationship to each other. And then the sample with all the elements is just sitting in between. And of course, because it's liquid, that's all moving fast. But what we have to learn out of this is we need an oxidic sample so that it can dissolve into glass. A metal or any reduced species like sulfide or nitrate or carbide is not able to interact with our lithium boron oxide. And therefore, it is very important to know that we need an oxide. Okay, but if we look on our periodic table, there are some elements which behave in a special way. And the first group is here from chromium to copper, because they reduce the surface tension of our melt, which then tends to sticking. That means our bead will release not very easy from the mold. And this is because these elements are there in a high concentration. Then we have volatile elements, of course, the halogens, fluorine, chlorine, we still can do by fusion, but we lose them. And the bromide and iodide, they are so volatile that we can't really analyze them in fusion, but they will be used as non-wetting agents. I will talk later about this. Sulfur is volatile, not as fluorine and chlorine, but we have to consider this. And sulfur is always a good indicator how stable your fusion system is concerning the temperature. So if you want to test your system, just fuse the same sample on all stations or burners, and you will know from the difference in sulfur how different the temperature is. Then we have elements which we can't dissolve into glass really, like the precious metals, and mercury also is just out of discussion here. We can't fuse that. Okay, but now let's talk about this elements which change the surface. So this one, which reduce the surface tension. So then it means that, like, for example, if a cement sample forms a bead like this with a concave surface, and this then releases much easier from the mold, these reducing elements, they make a convex surface, and then automatically these kind of beads starts to stick in the mold. And the only possibility you have to change this behavior is that you add bromide or iodide, so that in this way the surface tension comes back and it helps you to release easier from the mold. But be careful with these additives because they will make line overlaps. The bromides overlaps with the aluminum K-alpha line. So it depends on how much bromine you put in, but it's going pretty quick so that you need a line overlap correction. So you have really to be careful there. The same for the iodide with the titanium K-alpha. Here we are lucky because iodide is much more volatile than bromide, so most of this will disappear. But if you have too much in it, then definitely you also have a line overlap, and you need to do some corrections if you want to get reliable titanium results. How can we get the non-wetting agents? Either you have it directly in your flux, that means in the manufacturing it's already added, or you add it yourself as a solid, or you make a solution and you just add it by a few drops just before fusion. Okay, but let's now talk about temperature. If we look in a muffle furnace, we have the situation that your furnace is performing a certain temperature, so it's stable. But in the moment you open the door because you want to introduce a sample, the temperature has to go down, of course. So you destabilize the whole system. You close the door again, and then, of course, the system will reheat and will form again a stable temperature. But when you want to get it out, same story again, and the temperature will drop. So that means from the heating side, you have here stable heating situation, then you have to heat again, stable, heat again, and it's again stable. For the reproducibility of fusion, this is critical because in the moment you destabilize the furnace, you have to make sure that your heating is always working exactly in the same way. Yeah, and only if this is the case, and you fuse the same sample twice in a furnace, you will get the same result. If the heating of the furnace was not really designed for that, then you will have a big error in the volatile elements. So also the agitation is important. We have some system, they even rotate slowly in that phase, but when then the temperature is back, we then do really the agitation to get it homogeneous. And for the sample, if you look there, it is clear that here it is outside, it's solid. While it's then coming into the furnace, it gets liquid. And here you do the homogenization. And then afterwards outside, you cool to get a stable glass. If we look on a gas system, it's completely different because the system works from cold to cold. And the cold sample is sitting in the beginning in the machine. And then you heat and you increase the temperature. So this is then the ramp where the temperature is going up. The heat is introduced into the material, and then it will go from solid to liquid. And when it's liquid, we start there the homogenization. Here I tried to give you a relationship between the flux on one side, the temperature on another side, and the concentration or dilution of the sample on the other side. So a three-dimensional diagram. And the plane you see here, this is just the limit between over the plane, it is not working, and under the plane, in this range, you get a stable bead. Yeah. And I really try to explain a little bit how these three parameters work together. That means there will be a region where your sample is still dissolving, and there will be a region where you will not be able to dissolve the sample anymore. So this will define your dilution, your concentration. If you increase the temperature, you are able to dissolve more sample into it. This is why it goes up here. And then lithium tetraborate is the flux, which is able to dissolve the most of the material. And this means that while you change then to other fluxes which contain more metaborate, then it's reducing again, and then you have here a region where it's crystallizing. And I could say that this flux here, the 66 tetraborate and the 34 metaborate, this is a kind of universal flux because you see it's just in the middle. So it works more or less on all different kind of parameters here. And you have a very stable phase. And this is why if you start with fusion recipes, you should always start from this flux. Then it's quite universal what you want to set up. Okay, there are further parameters like the viscosity, which is of course defined by the temperature and the material, your sample. So if you have a refractory or you have a pure silicon oxide, it's a very high viscous sample. You need a very high temperature to get this homogenized. So this is also important. And of course, there will be the question for, in this range, when you have not much tetraborate as a glass forming agent, how much glass former your sample might contribute to your melt. And for example, the best is you have high silicon oxide samples if you want to use this flux, because then a part of the glass former is coming from your sample. So this is also an influence you have to take into account. Okay, let's talk about homogenization. And there are different systems in the market. Either you use, like our system, a circling homogenization, or some of other systems use the rocking. So you just go back and forth. If you want to be sure that your agitation is working, you could always have a look into the silicon oxide. And this is my experience, that this element is one of the most critical elements concerning your agitation. So you could always use the result of silicon oxide to verify if your agitation is good enough or not. And let's explain what this diagram means. It means that, for example, you fuse your sample 3 times, and then you calculate a standard deviation of silicon oxide. And then, for example, it's a very low standard deviation, a low repeatability. Then you are in a good way. That means your error is very little. But if you then reduce your sample, your agitation speed, then there becomes a moment when then your error of your 3 repetitions is really increasing, and then you know now it's not working anymore. So this is a very good indication, and I just indicated here that of course different samples with different dilutions need a different agitation. Yeah, and I have here an example of feldspar, which are sometimes difficult to fuse, and here you see if the speed is correct, we have a very small standard deviation. If the speed is not correct, we have a very high standard deviation. So very easy to find out. And then you can optimize that you increase your speed or you increase your dilution of the sample until you have a very low standard deviation. And then you are sure that your agitation is working correctly. Okay, platinum ware also plays a role. Normally we use platinum gold, 95 platinum, 5% gold. And the gold is used because it's also like a non-wetting agent. It avoids that your melt is sticking to the surface of the crucible, and the same for the mold. So it helps to release your bead from the mold. Typical melting point of platinum gold alloy is something around 1700 degrees. And then, of course, this is good for our fusion temperature range, which could be up to 1250 degrees. However, if you use, if you have in your sample metallic parts or reducing particles, then this will fail because immediately it will reduce the melting point of your platinum ware to a lower one. And if you come in the range of your fusion temperature, it will destroy your platinum ware. Some examples, sulfide, so not sulfate, it's sulfide, S or S2 minus, which reduces that, or metal silica, metal lead, they will extremely change the behavior. And then you have, like in this picture, you have holes in it. And if you're interested, you could have a look into the phase diagrams of platinum with these metals, and you will see this is the reason it reduces the melting point so that the stability is gone. This is for silicon and this is for aluminum as metal. Okay, let's talk about cooling. So cooling is also very important because in the end we want to get a bead, and this means it is a liquid which is becoming a glass. And this means that the crystallization is avoided. And this can only be done if you cool quickly down. Yeah. And we normally cool with pressed air. And this has a reason, because if you cool with air, immediately there is an air bubble formed underneath your melt and the mold, and this will help to release your bead afterwards, because while cooling down, the metal of your mold is of course shrinking, and this helps then even to release your bead. And so that's why air cooling is so an excellent tool. If you use a fan or you use just nothing to just let it cool down, then it will be completely flat. And this means it will stick, of course, much more to the mold, and you need more release agents to get it out. Yeah. So this is just that you know. You see that also that the beads in the end, you can test them on a flat surface, and you will see that this is a bit here not flat, but of course this is completely here over designed, so over exaggerated, just to give you the effect, to explain you why, if you use compressed air, the releasing is much easier than if not. Okay, some examples. For example, here I've used a lead concentrate, which was very difficult to fuse with this kind of flux. So you see here we have a part of crystallization, and it looks more than a ceramic. And if we change the flux, so we have more glass former, immediately you see that it becomes a bead. So here you see the difference using a flux with low tetraborate and high tetraborate, how this changes the glass forming behavior. The next picture is just dilution. So you see the color is gone. It's a bit lighter. I go back, you see the effect here, but it didn't help in this case. You see it's a bit more glass, but still I have here some crystallization, so not yet good. So again, the other flux behaves better. Here I have an example where I use a copper sulfide, so copper as an element which sticks a lot to the mold. So we get here a lot of tension, it will crack, and we add then some iodide to compensate this. And you see, as more you add, then suddenly you get a glass. And this is for iodide. And here I have another example with bromide, same story. This copper-based bead is sticking to the mold, and while this is shrinking in the cooling process, it just cracks. Yeah, when we add then bromide, it is stable and will release very easily. But here I also want to show you if it's overdosed. That means if we have too much bromide, we get this half moon effect, and then you have either to reduce the non-wetting agents, or you have add to more material. So that means you increase flux and sample to fill again the complete mold. So here, two examples, full crystallization, and this here is still glass, but so much tension that it breaks. So if you have crystallization, you can imagine that your fusion recipe is not optimal. Yeah. So your melt is not able to form a glass. The crystallization is much quicker in the cooling process. And this means that you have either too much metaborate, or you have a very poor mold, so that you have a lot of crystallization starting points in your mold. So this could be all reasons. While when you have then more tetraborate, you again become a glass. And tension means, like I mentioned, that it sticks to your mold, and then while cooling down, it's cracking. And then it could be that you should look for inclusions. So you have still particles which are undissolved. And this, of course, you can solve by grinding better your sample, by diluting, or by heating higher. Yeah, so these are all possibilities to increase the conditions, to get better conditions. So let's summarize this. What are our parameters we have to get under control? It's the flux, of course. It is the behavior of the sample. So how much glass forming it has itself, how much surface reducing elements it has inside. It's the ratio between sample flux, and do we need to add non-wetting agents? Fusion time is important, the temperature, which is of course also a function of viscosity, condition of platinum ware, how do we cool, and then of course also the agitation, homogenization process, is this really good enough? And last but not least, how distributes your temperature in the furnace so that all your crucibles get the same temperature. So this is all something which plays together, and which will influence if you get a stable bead or not. So that's it. That was really a fast ride through fusion technology. I hope I could explain you a bit all the parameters which are important. And now I'm a bit curious about your questions. You can post in the question and answer section here. And I see there is a first question there. what is a typical sample containing sulfur for checking melting temperature? I would say you can take a cement. Cement has up to 3% SO3. It's perfect, yeah. And then you just fuse this cement on every burner, every station, and the sulfur value will give you a directly answer on how good is or how big is the temperature difference between the different stations. There's another question. What do you recommend if I want to do calibration curve of press pellet in clays? Yeah, this has now nothing to do with fusion here. But of course, what you need is standard materials. You need to organize standards, clay standards. If you don't have them, you could use fusion to get the real values then for your powders. And with these values, you could then set up a press pellet calibration. So another question, how can I improve to avoid the formation of bubbles when I prepared fuse bead limestone? These samples are not calcined previously. That's a very good question because indeed, if there are volatile parts like carbon dioxide in your material and you heat that up, you form a lot of bubbles. And yeah, what can you do? The best is that you fuse longer in the hope that you fuse as long that everything is out, or you have to calcine first. Yeah, but we do limestone here uncalcined in our lab, and it works. So we have a certain time we need for fusion to get rid of all bubbles. So this, you just have to do it a bit longer. Perhaps you increase the temperature also a bit so that all the bubbles go out before you pour it. There's another question. Is the dimension of the platinum crucible and mold important in results, or does it depend on quantity of liquid? I wouldn't say that this is important. I mean, the mold must be as big that your bead is covering the X-ray beam finally. That is important, yeah? But if the X-ray beam is smaller than your bead, then of course you have it fully filled. There is a special case. You have to be careful that your beads are not too small. Sometimes people are doing the error that they have small beads and they're just lying on the margin then in the sample holder. And the margins is always a source of an additional error. So it's better to have a bigger bead, which is lying a few millimeters on the sample holder side. This gives much better results. So in this way, it would be good to use 40 millimeter beads to get very good results. Yeah. So another question, what kind of sample damaged the crucible? So it's metal samples, and it's samples with reduced species like carbides, nitrates, sulfides. So they are all destroying or attacking your platinum ware. So another question, what consideration I have to follow to do a calibration curve of aluminum oxide or bauxite? I would say this is a very straightforward application. So you could start with, let me say, with a dilution of 1 gram sample and 8 gram flux. Depends a bit on your fusion system. If agitation is not so efficient, you could perhaps dilute by a factor 2. But that's it. Use a typical flux, like I say, with 6634, and this should work. Another question. On platinum ware on the outside of the crucible, what can be causing a blacking of the metal that eventually ends up cracking from outside? There I have no idea so far. Perhaps you have to be careful when you take a hot platinum and you put it on any surface in your lab. If this surface is not pure refractory material and it's perhaps a metal plate, it could of course attack the platinum from outside. Otherwise, I have no idea so far. Another question, how to get specific analysis, especially sample with high concentration of SiO2. So I understand it in a way how to fuse pure quartz or high SiO2. You have to make sure that you have enough heat, because quartz needs heat, needs power, yeah? Because we know that quartz glass also has a high melting temperature, so you have to make sure that you grind your sample fine enough, that you dilute it good with flux, and that you have a fusion system with high temperature and a good agitation. Then it will work. Another question for gypsum: why not work with 8-gram borate, coarse crystallize? Yeah, that's a good question, why it crystallizes for you. I know that for gypsum we also use iodides as additive, and 1-gram sample and 8-gram flux, and this should work then. So then it shouldn't crystallize. You should use the 6634 flux, and then this should work. So I don't see why not. Another question: how important is weighing? What tolerance do you recommend? Weighing is very important, but more important is the dilution ratio between flux and sample. This must be correct, okay? The absolute mass of liquid or the absolute mass of your bead in the end is not important. But you always have to keep the ratio, let me say 1:8, to get a reproducible fusion. And the tolerance I would accept is the same than your relative error you allow. So if you allow an error of 0.2% relatively, then this is of course the max you should allow in the weighing. So another question: fusion method for chlor. How do you do that? So first of all, you can't pre-calcine your sample, because then the chlorine is lost. So you have to use a dried sample. And then what we do is we use a crucible with lid, so that we keep as much chlorine in the crucible during fusion and in the muffle furnace. Yeah, then it works, very precise and very reproducible. So it's on the same level than the wet chemistry titration. For example, chlorine in raw meal works perfectly in the fusion system. Another question: what should be done when the total sum of the elements exceeds 100%? Okay, there could be two reasons. First is your weighing is not correct. Then, of course, you have to change the weighing that the sum in the end gives 100%. The other reason could be that you have, for example, an iron compound like FeO, and this will oxidize during fusion. It will take some additional oxygen, and in this way, then your sum is, of course, higher than 100%. So this could be a reason. Or you have calcium fluoride in your sample. Calcium will, of course, also oxidize. So again, in the end, you will have a result higher than 100%. But of course, there is an explanation for that, and in this way, it's correct. Another question: is agitation as important for iron ore as it is for high silica samples? I'm not sure. I would say it's not as critical, but close. Another question: how to analyze pozzolan and not to lose SO3? So pozzolan, I made quite good experience. So you could fuse it like any kind of limestone or rock sample. It's very straightforward. And the SO3, you will lose a part of it, let me say perhaps 10%. But it's always the same. So if you keep your fusion parameters the same, the loss is constant, and then your calibration samples show the same loss than your unknown samples, and in this way you can perform a good analysis. Another question: what the optimal quantity we should use for the right fusion? I would say you should always start with a middle flux, the 6634, what I mentioned, and then a ratio of 1 part sample, 8 part flux, and then you start. If it cracks and it doesn't work, I would dilute first, and I would add perhaps some non-wetting agent, but do it always step by step, not at once, so that you get a feeling in what direction it will improve. Another question: can I prepare a bead with muffle furnace without hurling machine. Yes, of course. I mean, you can just use a muffle furnace. You put your crucible inside. And then, of course, you have to open it from time to time to agitate yourself. Of course, this open and close the furnace will make an instability. But I would say 20 years ago, everybody did it that way. So, of course, it will work. But you have, of course, to get used to it. Yeah. And then you have to preheat your mold as well. And you have to pour it then in the furnace into the mold and then take everything out. Yeah. So this would be the way. I know some arrangement where they preheat the mold outside on a burner, on a gas burner, and then take the crucible out and pour it. So different possibilities there. So another question here. Wow, there are many questions. For the oxidation agents that I can use for non-oxidized or semi-oxidized sample, and how are they added? I would say a very general oxidizer is strontium nitrate. Yeah, so you mix the strontium nitrate with your sample, and this mixture is placed on top of your flux. Then you go at a lower temperature, let me say something between 600 and 800 degrees into the furnace. It could be a standard muffle furnace, and you let it oxidize 10, 15, 20 minutes. Then you take it out. And then you go to a normal fusion system. Yeah, this is the principle how you can do it. Of course, you can do it also on the same fusion system, and then you need to arrange a program for that. But of course, you have to make sure that your oxidation is complete. Otherwise, you will destroy your crucible. That is, of course, always a part where you need experience. What oxidizer you can use for what metal. For what reduced species, that is the question here. Okay, last question. Some person work with sugar and not borate? I have never heard about this. So a sugar would be an organic compound, and it will disappear immediately. So it will have no effect on fusion, no help. So I think it will not work. Yeah, so this is not possible. And yeah, if this were all your questions, I'm very happy that you asked so many questions. Perfect. Yeah, I like that. And I want to thank you very much for these contributions. And I hope I could tell you a bit more about fusion and help you. You're always free to send me an email if you need any more informations. And so I thank you very much for listening, and I hope you join us again in one of the next webinars. Thank you very much. Have a good day. Thank you. Bye-bye.